Okay, so today I'm going to slightly reorder how we're doing this, just because we have someone here who's, Roberta, is here learning about pupilometry, because she's wanting to do a pupilometry study in the next couple of weeks. So I thought I'd start off with that first, then we'll have our break, and then we'll go back into using the data viewer for the other properties. That way you can disappear after we've done the pupilometry. And I'll also explain just after the break about how you install these keys on the computers. Especially if you have a Mac or a PC, there's just 1 or 2 steps you have to do to actually make the keys recognizable. Okay, so pupilometry is, in many ways, is one of the older forms of eye tracking, or reasons why people track their eyes in terms of research purposes. It's also the one that is, the analysis tools have been very primitive for a long time. That's changed in the last few years, and as people started to, and researchers have started to index how pupils change size as a function of different cognitive states, then this has become a very useful tool because it gives you a very quick and effective way of assessing things like workload online. So as your participant is actually doing a task, you can actually use the pupil size changes as a function of measuring their workload or attention. And so, how many of you have seen the old Blade Runner movie where they kind of hook the person up and they have an eye thing, and that's basically pupilometry. So the idea of getting people to tell the truth. When you lie, there's a pupil dilation, which is really easy to avoid. And I'll show you how to lie and avoid that today. So just a bit of brief history about pupilometry before psychology. So you can kind of go back to Cicero in Greece, who was the first person to sort of philosophize that the eye is the window to the soul. It was around that time where the pupil was first referred to. In fact, it comes from the Latin pupilli, or little doll. The idea is if you look in someone's pupil, you can usually see a reflection of the real world, but much, much smaller. And those crazy ancient Greeks were interested in playing around with all sorts of drugs and putting them into people. So Galen, back in 129 AD, used plants to actually dilate the pupil while studying cataracts. So even as early as that, the people were starting to find things, a way of adjusting your pupil. In fact, you can go back to if you fast forward a few 100,000 or 1,000 years, you kind of go to the French Revolutionary time. Women in the court would actually use atropine, which is a plant extract, to make their pupils look larger because they felt like that having a big pupil made you look attractive. You can even fast forward to today's times where you look at sort of a lot of these Japanese manga anime characters. They all have big eyes. If you want to look cute and attractive, apparently you have to have a big eye. And that really comes from that sort of the French court days. At the same time, people started, were starting to say, okay, well, what's happening with the pupil? And so both Archimedes and Galileo independently developed different measures of pupil size. So Archimedes actually based it on a series of metal tubes of different diameters, and would look through the tube and sort of match it up to the size of the pupil. Galileo did this in a much more simpler way with using pieces of paper of different sizes, would kind of move those in and out to see which size matched the pupil size. You fast forward to the mid-60s, so along the time when eye tracking was starting to sort of develop, well, individuals were creating what were called pupilograms. So what it was is basically a movie camera which just focused exclusively on the area of the pupil. And so as the film recorded the pupil size, you could kind of play that back and show the change of pupil size as a movie, as a video. Unfortunately, none of these are on YouTube yet. So if anyone does find them, let me know. I'd love to show one. Now we've already talked about the pupillary response in terms of this light response. So obviously, this idea that the pupil changes size as a function of the light that falls upon it is not new. In fact, you can go back to Razes in 1850 to 923 AD, who first sort of described and actually in a methodical way described the pupillary light reflex. So, just to remind you all, this pupillary light reflex is that, in a normal situation here, when we've got a bright light, then the iris around the pupil constricts, making the pupil much smaller. In a medium light, as we start going to lower light level conditions, then we start seeing a dilation of the iris, allowing more light to fall upon the back of the retina. Now, that extreme goes from the smallest point we can usually have in most people's eye, where the pupil the iris is fully constricted, so the pupil is its smallest, would give you a pupil diameter of about 1.5 millimeters. If we put you in a dark room for a period of time and actually measured your pupil size, the largest is around about 9 millimeters. So we're talking about a reasonable change which you could actually pick up with one of these pupillometry type meters, or a film camera. On average, most people's pupils will be at the sort of middle level of around about 3 millimeter in resting daylight situations. So in here right now, your pupils are roughly speaking about 3 millimeter in diameter. When you onset a stimulation, so if I shine a light in, actually, Karen, can you just go in my office under my computer? There's a little light.
On the computer?
Under my Mac there. There's a small light pen. So when you stimulate, so if I have a dark light and if I shine a light into someone's eye, that change from fully dilated through to sort of a constricted takes about 200 milliseconds. So it's not an instantaneous change. It's a change that's occurring over something that we could quite easily measure. So how the pupil changes in diameter and during this dilation and constriction is actually because the iris itself is actually made up of two different sets of muscles. So here you've got the actual iris itself. On the inside here, you've actually got a series of circular sphincter muscles, which will contract under parasympathetic stimulation. So we'll actually sort of contract in and sort of squeeze the pupil to be smaller. And then obviously when that happens, as the muscles start squeezing smaller and smaller, the pupil gets tighter and tighter. Okay, thanks. So just to show you, this is something you can buy for about $1 on Amazon. This is, if you're a clinician, this is one of the simplest tools you can have in your arsenal. All it is a simple light source. So what we can do is shine that on someone's eye, hit the top of the pen here, and I can shine a light into someone's eye. What's also great about it, it has pupil sizes in millimeters, so I can actually, at the same time, I can then see what size is the actual pupil contracting to. So in this case here, this is graded from 2 millimeters up to 9 millimeters on the side. $1, it includes batteries. So this is a great little tool to have just in order to see if you want to do a pupillary response on someone, just make sure they have a pupillary response to light. If they do, that's a good sign. A little trick. So that sphincter muscle will squeeze and contract the iris, correspondingly making the pupil much smaller. Now, to dilate, we actually are under sympathetic stimulation. So in this case here, we have a second set of muscles, and these are actually radial muscles that attach onto the sphincter muscles, and these are what we call dilator pupae muscle. So you see these sort of muscles string out, and they actually pull the sphincter out. So what it does is it pulls on the edge of the sphincter, as a corresponding, it makes the pupil larger by unfolding and unwinding the actual the sphincter pupillary muscle. And that's under sympathetic control. So when the two work together, we've then got a way of causing quite fast constriction, at the same time quite fast dilation. But importantly, these are under two separate stimulation conditions, either parasympathetic for constriction or sympathetic for dilation. Now, the actual control of those is actually controlled by this area here. This is what's called the lotus coeruleus, or area LC. And this area is also very tightly, it controls the noradrenergic system in the entire brain, but it's also highly involved with a lot of different psychology processes, in particular things like stress, memory, selective attention, and general arousal all seem to cause activation. In animal studies, they've shown that those sorts of stimuli or psychological processes will cause activation of this area LC, which in turn links to the pupillary response. So it's really this area LC is responsible for a lot of that change that we observe in pupil size as a function of psychology. Interesting as well, there seems to be two separate modes in which it works. And this we'll come back to later on when we actually look at some pupillary response data, is that it really seems to be two separate ways in which pupillary responses occur. The first is a sort of a phasic mode. That is a very rapid change in pupil size, usually designed to optimize during a specific task or a specific response. This is what usually leads to a rapid dilation of the eye and at the initial onset of a stimulation. After that, the mode switches over from that sort of very quick response to a sort of more sustained long-term response, which is what's called the tonic mode. This seems to be associated with elevated firing in LC, and this causes the more sort of long-term dilation of the pupil. And seems to be, again, there's various research which shows it helps promote disengagement from a task, or more sort of general exploration of a particular task or scene around you. So there's this sort of that quick change in pupil, and then there's a more sustained response afterwards, which comes from this second set of firing patterns that come from LC.
Can you go back to your slide, a couple of slides earlier about the parasympathetic and sympathetic? Yes, this one.
Yes.
What is it? I'm trying to grasp why the contraction is solely the responsibility, if I can use that term, of the parasympathetic system, and the dilators aspect of is attributed to the sympathetic. What makes it that they're not the sympathetic cannot do both and parasympathetic cannot do both?
It's a good question. There is a lot of physiology to explain this. So you can block either sympathetic or parasympathetic stimulation using various drugs. So atropine is an example of one of these. In the Dropbox, there is a older PDF document called Pupil Response. In there, this is from the late 80s, but it seems to be the best. It has a long explanation as to the experiments which they used to discover those two. Today, I don't have as much time to go into that, but if you want to know more about the pharmacological neural mechanisms and how they connect, you can read up in there. That's why I put that document in there. And it's an older chapter from a book, but it really does have a good explanation of how we think it works. There's a lot of other studies which are happening at the moment trying to sort of quantify it, because especially now that pupillometry is becoming a very popular technique in psychology, a lot of researchers are trying to better understand the mechanisms behind it, but it's still a bit up in the air. So if we look at, we have these pupillary changes in pupil size, but obviously, LC we've shown that it relates to some psychological processes. So again, very, very quickly, I'm going to go over some of the sort of papers and research which have looked at pupillary response in the area of psychology. So for these, I've also put the originals. I don't have some of these in the Dropbox just because a lot of these earlier papers are from the 40s and the 50s and the 60s, and we can't get electronic copies. If you're at all interested in getting them, you can probably get them through Interlibrary Loan. So if you go back to 1943, so Barron and Huntington, really, I think, most researchers agree this was sort of the first scientific study which linked psychological processes to pupil dilation in a meaningful way. So they actually used a very focused telescope looking at the eye to assess the emotional effect of lying. And what they actually showed is that there was a very specific pattern of slow dilation and then a quick constriction immediately after that, which was associated with an increased rate of deception. So the more you lied, what initially happens is you get the sort of slow dilation of the eye as you start lying, and at some point they observed this quick constriction of the eye during that task. So this shows is that when you're looking at the pupillometry, it's not only important just to look at pupil dilation. In some cases, you may also get constriction, and we're going to come back and talk more about that later on. Some of the sort of the real sort of pioneering work, though, was done by Hess and Palt. They had two papers which were published in Science back in 1960 and 1964, which showed that the pupil size could be used as an index of specific interest or attention, and in mental load. So in terms of attention, they did a very simple thing. So what they did is they had heterosexual males and females look at photographs of nude males or nude females. And what they found was that when men are looking at nude males, there was no change in pupil size. When they were looking at nude females, there was a dilation of the eye. Conversely, women observers, when they were viewing photographs of nude women, showed no pupil size change, but when viewing nude males, again, they showed a pupil dilation effect. Third, this mental load, what they were doing is doing some very simple problem solving. In fact, we're going to use an example from this later on to show you how you analyze pupillometry. But basically, they just get people to do some very simple mental arithmetic, either very easy or incredibly difficult. What happens is when you give people a difficult task, you get a very quick and immediate pupil dilation, and which sustains for a long period of time. So when I was talking about how you could lie and cheat your way through a pupil exam like in Blade Runner, easiest way to do it is just do some mental arithmetic. If you do some mental arithmetic, your pupils are not going to change size. They're just going to dilate and just stay dilated for a long period of time. So now you know how to cheat a eye pupillometry detector, lie detector. Again, a lot of this, there's a lot of repetition in the 60s. So again, this sort of idea of when pupil size being larger when viewing pictures of interesting visual stimuli. So nudes versus clothed. When you're viewing nudes, your pupil size dilates. When you're viewing clothed individuals, you get less dilation. There's also been some other, beyond visual stimulation, other psychological processes also show an impact on pupil size. So, for example, when people are tasting food that they find preferential, or are listening to music which they find more enjoyable, pupils dilate faster than if they're eating food or listening to music which is not of as much interest. This pupil dilation seems to be linked to something in terms of, if you take the visual stimuli and then these other stimuli, it seems to be an index of something about our liking or our preference for particular types of stimuli.
It kind of goes back to what Michelle was saying with regards to sympathetic and parasympathetic, with regards to when we go into our sympathetic activation, it's more of a heightened state, arousing state, versus the opposite, where the parasympathetic response, which would seem to be in concordance with what you're saying with regards to even just food preferences.
Yeah. And I mean, this is collectively, this all points to this. It's just that there are some very specific experiments which actually have mapped out the two, but again, we don't have time to deal with those today. There are also, it seems to be linked to pupil dilation seems to be an analog of pain perception as well. Not only actually receiving physical pain, but also subjecting people to stimuli which reflect pain. So, if I put up a photograph of a dentist pulling out someone's teeth, and they're doing this with a jackhammer or something, which is like, and there's blood going everywhere, something from a movie, you're obviously going to kind of go, ew, that's horrible. Likewise, you actually get a pupil constriction to those kinds of stimuli. So it's almost like you're trying to reduce the image on your eye by constricting the pupil. In terms of exact psychological processes, then there are a number of different areas where pupillometry has been used quite effectively. So let's start off with cognitive load. So this idea of, as we do certain tasks, some of them require more cognition and thought processing than others. So again, you can go back to that Hess and Pult study, which showed that as you increase the difficulty of math problems, you get more and more pupil dilation. Others have shown that it's a measure of sustained attention. So if you're doing a task that requires you to concentrate on the task for a long period of time and attend the task, then again, what you see is the more sustained the attention, the more pupil dilation is observed. Others have done this with working memory. So keeping a series of sequence of numbers in working memory, the longer the sequence, the faster you get a change in pupil size. So if it's a 3-digit sequence, you don't really get much of a pupil size change. As you start increasing to 7, then you get a pupil size dilation, and then if you go to 12, then you get a very quite rapid dilation of the eye. It's also involved in decision making. So this actually was a task that was done with pitch discrimination. So where's the pitch going up or down? So very, very simple task where you have to discriminate, was the first tone higher or lower than the second? So in terms of a choice task, this is very simple. As the differences between the tones becomes less, obviously the task gets more difficult. And so it becomes more difficult to actually make a decision about whether was the tone going down or up. In those situations, again, what you see is as the task becomes more difficult and the decision gets harder and harder, you see an increased pupil size as the task becomes more difficult to make a decision on. If we look in the area of just basic perception, so like I said, we have the light response, which when we shine a light into someone's eye, then we get a nice pupillary response. But what's also interesting is if you have an illusion, which is light brightness based, or even a suggestion of a decrease in brightness of a stimulus, you actually get a dilation of the pupil. So it's almost like if you give people saying, well, I'm going to give you something now, it's going to grow darker, even though it's actually staying the same, they will actually show a pupillary response as though the stimulus were getting darker. In fact, the Lang and Endestad paper in 2012 showed that if you actually physically change the light level and then psychologically trick people into thinking that light level is reduced, the pupil respond in exactly the same way. So it shows that even though that pupillary light response, some of it is a physiological mechanism to change the amount of light on the back of the eye, on the retina, this can also be overridden quite easily with simple psychological cueing. Attentional blinks. For those of you who are not aware of this paradigm, what you can do is you can kind of show a series of rapid presented stimuli, and you can, if you insert, say for example, if I told you to find, was there a giraffe in a stream of images? And I show you a rapid stream of images, and I show you a giraffe. You'll cognitively encode, hey, there's a giraffe there. If I present another giraffe that's different immediately afterwards, or quite close in the sequence immediately afterwards, you're actually blind to that second presentation. And what's interesting is when you do this with pupillometry, you find that both the latency and the amplitude of the pupillometry response corresponds to that correct detection of the first and the missing of the second stimulus. So they're actually quite connected to each other. And again, there's a lot of studies which are out there which show that if you have endogenous or exogenous attentional cueing paradigms, again, those show differences of pupillary response. So there's this paper in 2013 by Gaver and colleagues, which showed that different formats of attention and attention allocation cause very different patterns of pupillary response dilation in participants. Okay, language. Language is an area where a lot of pupillometry response. In fact, if you actually, like all eye tracking, if you go back to the 60s and 70s, most of the first pupillometry papers came from and out of the area of language and reading research. So pupillary diameter appears to be a function of speech, intelligibility, interference, and it also seems to predict a lot of alterations in verbal language. So if you ask people to say either a simple sentence versus a more grammatically complex sentence, you see these differences in pupil size, again, reflecting the more difficult the task, the more pupil dilations observed. Pupil dilation also has been shown to be a very good measure index of word difficulty and retrieval, especially in bilingual participants. So if you have individuals and you give them an easy word to retrieve, which is used more frequently in each language, versus something that's more complex, that's maybe only used in one of the languages, then at those more complex words, when they land on that word and they're trying to recall the meaning of that, or if you're dealing with a situation where a word has two different meanings in each language, then you start seeing this quite fast, rapid, and sustained pupil dilation in response to the fixation on that word. This is a fairly recent paper which showed that as people start wandering their attention, so you give people a reading task, are they really sustaining their attention over the entire time, or does their mind start to wander? Well, again, sustained attention would lead to pupil dilation. What we find is that during reading tasks, as people's attention start to wander, the pupils start to constrict, and that corresponds with them sort of not focusing on maintaining that sustained attention on the task. And again, memory and decision making, pupil dilation appears to be a very good index of the process involved in decision making. It doesn't really tell us anything about the outcome, just more in terms of how difficult the decision was. It's a relatively easy decision to make. There's very little change in pupil size. The more difficult the decision becomes, the more the dilation we observe during that decision-making process. But it doesn't actually correlate or relate at all to the outcome of the decision. Pupilometry is used a lot in the last few years in terms of rewards and reward cues. So again, if you give people a reward by saying, okay, I'm going to give you $100 if you get a right answer and take away $1 if you get a wrong answer, people are going to be focused, again, maintaining their attention, so you have that focused attention to really get this right, leading to an increased pupil dilation. The other area where it's been used a lot as well is to actually measure online stress levels during the task. So if you give people a task to recall a specific type of memory, and then you give them an unlimited time, then again, people tend to not show up pupil response. As you start giving them a time constraint, so really you're stressing them out because you're saying, okay, you've got 10 seconds to recall a specific memory. Now, what we start observing is this increased dilation of pupil size as a function of stress. The more stress you give, so the more reduced time you give people to make a decision in, the faster the pupil dilation and the more sustained it becomes.
It seems to me that pupilometry is pupil size varies by a function of so many things.
Yes.
That I feel sorry for you because you're doing research in this, because I think it varies. Pupil size varies in so many, according to so many things, that it'd be very difficult to isolate what you're trying to measure, and B, develop in your paradigm, something that would counter measures.
So it is, and I haven't even got to the hard part yet, okay. Or the most of the. But again, what I'm hoping to do is show you today is that if you do this right, you can do this in a methodical way that does show real differences, and you can actually control or at least link it to your design of the paradigm that you're interested in. So I'm going to show you how you can do this. In terms of, again, emotion and cognition, pupil dilation is observed when participants view arousing, so either positive or negative images relative to neutral images. If it's very negative, though, like I said, you get this sort of pupil constriction often. Pupil dilation also occurs a lot when you're having face-to-face interactions, particularly when you're aware of other people looking at you. So if you're doing, they did this with a study where they recorded eye movements while watching a video where the person did not make explicit eye contact. when the person made eye contact with the observer and looks directly at the observer, you actually see an increased pupil dilation. So this may have something to do with empathy or emotion detection in others. Again, there's a lot of correlations been shown between pupil diameter and rating of the pleasantness of faces. So if the more pleasant the face, girls, if I show you Ryan Gosling, most of you would show a nice pupil dilation in response to Ryan Gosling. And again, just relating this back, a lot of researchers have shown that sexual orientation also while viewing erotic images. So, like I said before, heterosexual will tend to prefer the opposite gender when viewing and show a pupil dilation. However, when you do this within individuals who are homosexual, then they'll actually show a pupil dilation to the same gender that they identify with. So if we have a homosexual male, they will actually show a pupil dilation to male nudes, but not to female nudes, which is opposite to heterosexual males.
So it seems like when you put images that are more dark or more white, like you get these effects of the pupil dilation.
Yes.
It's basically why you have a black rooms upstairs.
Yeah. We're gonna get to this in a bit as to how you can factor out some of this. So, as Michelle was saying, pupillometry, there is so many things that be causing a change of pupil size on top of all the light responses that you could have, and it gets worse. But let me just finish this off, and then I'll explain the really bad news, but then how we can get around some of this. So finally, in developmental research, pupillometry is really the hot tool right now in developmental research. Obviously, when you're dealing with infants who you cannot ask them specific questions often, you're looking for sort of an online measure of what might be going on inside their little brains. Most of the recent research, in fact, most of what's driving the pupillometry analysis at the moment actually comes from developmental research. Again, pupil dilation seems to reflect this emotional processing in infants. So when you get them to sort of predict an outcome of an action, you see the sort of, or when you start looking at emotional development, so theory of the mind. So when children start developing a sense of emotion in others, then you start seeing this quite dramatic pupil response, dilation response, when you give an emotional stimuli, compared to young infants who just show no response at all. So it really does seem to be an emotionally driven response. Again, some have looked at this in terms of intentional actions between sort of 7 and 12 months. At 7 months, infants don't show this pupillary response when doing a specific action, but by the time you get to 12 months, they actually show that response. Again, this allows you to get some sort of measure of what might be going on, or how particular things like emotion detection, theory of the mind are developing in very young infants, where we can't get very objective measures of what they're actually thinking. Somewhere linking this back to pain, some research has shown that in adolescence, when you start looking at peer rejection versus peer acceptation, when you're rejected by your peers, you actually show a pupillary dilation response, which, again, if you think about it, peer rejection can be painful, particularly amongst adolescents. And so that psychological aspect of rejection kind of relates to pain, also relates to this pupil dilation. They show a quite strong, rapid, and sustained pupillary response when placed in these peer rejection scenarios. Okay, so yes, it's been used in psychology. It's been used, and this is just a snapshot. There are over 100,000 papers on Google which if you type in the words pupillary response and psychology, it comes up with everything in the kitchen sink. So some things which are worth noting, which we often see. So when you do a luminance variation, you tend to have quite a large pupillary response. So it goes from the full 9 millimeters down to sort of 1.5 millimeters. When we're dealing with any sort of change due to cognitive load or arousal, these tend to be very small changes. So by small, I mean we're talking about dilations or constrictions of around about 0.5 to maybe 1 millimeter. So the pupillary response to a lot of these psychological processes tend to be much smaller than a light response. That's the first thing to consider. Secondly, although generally involuntary, people can induce dilation by mentally manipulating their thoughts. Again, if you want to lie or cheat one of these tests, either do mental arithmetic or think very sexy thoughts. These tend to be the very easiest way to cause a rapid and sustained dilation. However, at the initial response to a stimulus, it's very hard to inhibit that initial pupillary response. So this sort of way of dilating works well over a long duration, but in terms of the initial onset of the stimulus, we have no control over that. It really is an automatic response to the image. Over a long period of time, and again, this links to this general observation in eye tracking studies where after about 20 minutes of continuous tracking, people's eyes start to behave differently in terms of patterns of eye movements where they look. Well, when you actually look at the pupillometry, this is observed again and again, that after about 20 minutes of eye tracking, the average size of the pupil actually starts to decrease. So the pupil, you actually get more and more pupil constriction over time. So if I plotted pupil dilation over 20 minutes, it would be fairly stationary to begin with in terms of the average, but over time you would start seeing a reduction, a constriction of pupil size over time. Now, what's also observed in a few studies is that as you start going into the later trials, you actually start seeing more variation of fluctuations of pupil size. So at the initial onset, again, if you think about this in terms of sustained attention or concentrating on a task, people tend to be very good at the beginning of an experiment. Later on, as attention starts to wax and wane, people get bored. They're like, when will this be over? Can I go to the toilet? Can I have a cup of coffee? I need to concentrate on this trial. There's going to be more and more fluctuations in the pupillary response. So you may not get as good a quality pupillary response at longer durations of trials. So again, keeping that as a rule of trying to keep any one block of eye tracking under 20 minutes is a good rule, because after about 20 minutes, you start seeing more and more of this sort of fluctuation in response.
I've got a double-edged question. Could it also be on your fourth point about 15?
Yeah.
Could it not also be a question of habituation? Sokolov's idea of habituation.
Yes. It could be something.
Are you hinting at fatigue as physical fatigue or mental fatigue?
Some of it could be physical fatigue, it could be mental fatigue, it could be habituation. Researchers have shown all three. Okay. It's just something to keep in mind that if you are planning on doing a pupillometry, make sure you keep the overall experiment fairly short. Or make sure you put in breaks into your experiment to allow people to recover and get back to more of that normal performance. Get them to do a filler task. Get them to sit there and watch Bob Ross painting. Get them to do something that's going to relax them and get them back to a more normal functioning of pupil response.
This brings me back. My second question is just exactly that. Is there an agreed upon time limit that where we on breaks where we see that this fatigue will wane and the tension will come up? Is there an agreed upon time? 5 minutes, 10 minutes?
No, there's no agreed upon. So roughly, the rule of thumb we have in my lab is 20 minutes of eye tracking must be followed by a 5-minute break. That seems to be a good. I don't know what Deborah's lab, if at all.
About 2 hours, and then we give them a
Yeah. So that might be. You might look at actually how your eye tracking changes over time in terms of pupil response and eye movements. Because what you find is that, like I said, people start moving very strangely. After 20 minutes, that's where you start seeing this rapid change in like eye movement variability. So people just stop moving their eyes as much. So the overall variability of eye movements go down. Pupillometry seems to go, that's where it starts going very weird, is after about 20 minutes. So as a rule, 20 minutes in a block, give them a 5-minute break at least. That's a good sort of balance. 5 minutes is enough that lets people recover. You also don't get as much eye strain as well, looking at a computer screen. Now, on top of all of this, there's also the problem that eye trackers introduce errors in pupil size estimation as a function of where they look. And by some, it varies in every eye tracker does this. It varies into how much depending on the type of eye tracker. So what am I talking about? Well, I'd shown you this figure back in week 2. This is looking at the calibration of the eye at the 9 different standard calibration points. So if you look at the center over here, so the center in the middle of the screen, you can see we have a nice pupil, our pupil is nice and circular. As we start moving up and down, we actually get compression in that oval shape. Likewise, if we move left and right, we get compression in the vertical. So we start seeing it becoming more oval-shaped in this way. Obviously, at the extremes, you've got a combination of both. Now, in terms of pupil size, the pupil size is changing in all of these screens. And remember, pupil size is being estimated based on the 2-dimensional infrared image that the actual camera it has. So most eye trackers will calculate the area of the pupil and use that as your pupil size, or we'll actually convert this into a horizontal and vertical size. So if you have a Tobii, that's what it does. It actually converts it in terms of a pupil size in terms of height and width. As a consequence, even just getting them to look at dots, there's no cognitive load here. The pupil size here is going to be different in both the horizontal and the vertical height in comparison to the center. Okay, so this was actually shown quite effectively back in 2013. There's this paper by Brissan and colleagues. In fact, Sylvain Silvoire, who's at the University of Trois-Rivières, is kind of pupillometry god in Canada, if not the world. He's published a lot of research on pupillometry data, especially in infant research. So if you're a developmentalist, you should definitely read some of his papers. He showed this quite effectively and showed it across 3 different eye trackers. So on the top here, we have a Tobii T120. This is like an older Tobii. On the middle here, we have a Tobii X120, so slightly more update model. And then on the bottom here, you have the iLink 1000. What you have here are changes in pupil diameter as a function of where they're looking at the screen. So what they actually do is they put up a circular target that moves around the screen at different locations. Anywhere that's red marks that the actual pupil size is larger than what it should be reported. Anywhere that's blue, it's recording it as being slightly smaller than it actually is. And then each dot represents where the actual eye was positioned while it was being sampled. So first of all, you can see the sampling accuracy of the older Tobii is quite poor in comparison to, say, for example, the iLink. Remember, the iLink is a much more precise eye tracker in terms of how good. So we would expect it to be closer on that ring. But what you also see is a huge amount of variation in pupil size as a function of where you're looking at on the screen. And you can see that quite clearly in all three of the eye trackers. So that's a worry, because now a lot of research studies, especially those in the 60s, 70s, 80s, and 90s, did not think about the fact that the eye changes size depending on where you're looking. And this is a kind of a, this is a sort of a mic drop moment in eye tracking, because it really was like, oh gee, a lot of the research out there may be explained quite easily by the fact that they're just changing pupil size depending on as you're tracking or where you're looking at on a text. So if you're reading a text from left to right, you're going to have a change in pupil size as you go across the page. So raising questions about how difficult pupillometry is, yeah, it's even more difficult because you have to take into consideration where things are. So how do you get around this? Well, first of all, the easiest way is just to make them not move their eyes. If you want to show up an image and just get a pupillary response, or show a stimulus, so if you've got a series of tones or an image, get them to look at a fixation point, put the image up, make them maintain fixation on a single point. Throw out eye movements altogether. They're not moving their eyes. The pupils are not going to change as a function of where they're looking at the screen. It'll only change as a function of what they're looking at. That's the simple solution. The other way is you can actually map out these changes of pupil size across the screen and correct for them in your analysis. So again, how do you do this? And this all comes from this paper here. So what you can actually do is what we have here is the three eye trackers. This is the coordinates on the horizontal and vertical scale for the Tobii, the older Tobii, the more up-to-date Tobii, and the iLink. What you can do is do a simple linear regression to quantify the relationship between the gaze and the pupil diameter. You can then use the coefficients from that linear regression to correct for the bias or the change in pupil size as a function of x and y on the screen. And when you do that, what you're doing then is removing the change in pupil size as a function of where they're looking at the screen. Whatever's left over should be either due to the light response of looking at a lighter or darker part of the screen, or what you hope is linked to the actual psychology response. Yeah, so what you can do is, you're simply fitting a linear function here to each of these samples here reflects one sample where they were looking at the screen, standardized and offset depending on where they should be. So what you then have is a variation in gaze point and a variation in gaze parameter. You can just fit a simple linear function. You can do this in Excel, R, MATLAB, SPSS. You get your three coefficients for your function, your linear function, and you just plug those into this formula. So the pupillary response is the pupil size minus the bias in the x multiplied by x, the bias minus the bias in y multiplied by y, and that modifies your pupillary estimation to compensate for the change in position. And if you go to their website, they actually give you code to do this in MATLAB. So very nice people. So you can correct for this. So option 1, don't make them move their eyes, look at a pupillary response. Option 2 is to correct for that bias. Okay, so how do you go about doing a pupil analysis? So what I'm going to do here, this is actually from Sylvain Savoy's website. So he actually has data up there that you can kind of download and play with. So this is a very simple, old school experiment. We're going to do a simple mental arithmetic task. We're going to have 8 participants, 5 female, 3 male. They're all aged between 21 and 42, so kind of a usual university group. They have to carry out 2 mental arithmetic tasks. 3 are considered to be relatively easy. That is, they're additions that don't require carrying over. So you can add these up without having to carry over values to the next column. 3 are considered to be more difficult. That is, you're going to have to start carrying numbers over while doing the additions. If you do this with undergrads, by the way, which we've tried, they find the easy problems difficult to do. It's kind of sad. But you also only give them 10 seconds to do each trial. These were actually, all the data which is on there was recorded on a Tobii eye tracker at 60 hertz as a binocular eye tracker. So this is what a trial actually looks like. So you would put up a fixation point. It would be up to 10 seconds. You can try doing this yourself. This is an easy one. For those of you who are not sure, that's a more difficult one. So each case, it goes back to a fixation point for a period of time, then transitions out to the easy. So in this case here, we're just doing easy, difficult, easy, difficult. This is what the raw pupillometry data looks like. So each line reflects an individual subject. This is for the 3 easy conditions. This is for the 3 difficult conditions. What we have here is time on this axis here, and on the vertical axis, you've got the change in pupil diameter. Now, Tobii actually convert this to millimeters for you. If you do this with a system that does, so some systems don't do that. Some systems will only give you it in arbitrary units. So for example, the iLink upstairs will only give you it in arbitrary units. There's a good reason for that, and that is because the pupil diameter will change depending on the viewing distance each time. So what iLink do is they make you do the work and actually calculate it for yourself. Very easy. If you want to convert it to millimeters, what you do is you take something like this, or you print off a piece of paper with a series of black filled in dots of known sizes. So you print one off and you have it, so you have one that's large, medium, and small. You place that where the iLink, the person would sit, and then you can get the arbitrary units of each size. And then you can just convert between your arbitrary units. You fit a linear regression to the response to those 3 sizes, and then you can just convert them to millimeters. Not that difficult to do. And again, if you have a pen like this, you just hold this up and you get it to do it for you. Okay, so in this case here, it's in millimeters. So remember I said changes in eye movements due to mental task or psychology tend to be very small. So if you actually see here, you see a lot of these variations in eye movements. If you take this guy here, its subject, they got a variation there, but it's less than half a millimeter. So we're talking very, very small. The other thing you can see is that there's a lot of incomplete data. This could be because someone's blinking, there's a failure in the sampling of the eye tracker, someone looked away, they moved something in front of their hand, whatever. Pupil data is never incomplete. There's always going to be gaps in the data. Okay? Finally, you can also see that there's a sort of a trend in the participants in that some of them have quite a large pupil size, resting pupil size, and others have a sort of smaller pupil size. So, incomplete data, a lot of individual variability. Why would anyone want to study pupillometry? Okay? And it changes as a function of position on the screen. This is typical pupillometry data. So to deal with it, you either have to do a lot of averaging, or you can actually sit there and methodically clean up this data. So how do you do that? Well, let's just take this example here. Here we have just a hard condition. Again, this is quite nice because, again, you see that separation between the two groups. You see that we've got this incomplete data here. Well, first of all, how do we deal with this incomplete data? Well, we've got two eyes. So if someone's blinking with one eye or the other, the pupil size in both eyes correlate highly with each other. So what you can always do is take the pupil data from one eye and use it to fill in the missing information which is missing from the other eye. Or average between the two eyes so that it fills in the missing information. That's great if you've lost data on one eye or the other. If you're only recording from one eye, or if people are blinking both eyes at the same time, that does not help you. The other thing you can do, and again, this was proposed by Sylvain Sawar back in 2009, and is really kind of the gold standard right now in pupillometry, is that first of all, eye tracking pupillometry data, as you see, is quite naturally quite noisy. The very first thing you want to do is get rid of some of that noise. So what you can do is apply a low pass filter, so a 4 Hz filter, will remove a lot of the high frequency noise, leaving you with smoother data. Once you have that, then you can do linear interpolation to fit the missing information, or fill in that missing information. When you do that, this is now what that hard data look like. So you can see it's starting to look a little smoother and a little easier to find trends in the patterns of eye movements. So that helps us fill in the missing information and makes the eye tracking data a little less noisy. Now, the other problem is that we've got two subsets of participants there. So the other thing which we often do is we actually will normalize the data based off of some baseline. We'll sort of baseline correct it. This actually comes originally from EEG research. So EEG research, everyone has different electrical potentials over time. What we're looking for is not just a raw change in eye movement. What we're looking for is just a change relative to where it was before. So what you can do is take a period of eye tracking data immediately before the onset of your image. You're all using drift correct fixation points. Hey, you've got some nice stable eye tracking data where they're not moving their eye. Guess what? Perfect for getting what is the sort of the average pupil size of your participant at that moment in time. What's great about this as well is it also avoids that change in pupil size over long durations, because in each case you can normalize this based on the onset of each trial. So normally you would take a period of time just before the stimulus appears, at least 100 milliseconds worth of sample data. So on an eye tracker which is tracking at 60 Hertz, that's about 6 samples worth of eye tracking. If you've got more the better, that you have a much better average data. So if you've got half a second of eye tracking data from a fixation point, perfect. Take the average pupil size while looking at the fixation point, and then subtract that from all the eye tracking data while they're viewing the image. When doing that, what you see is all the eye tracking data then normalizes are just near zero. It may not be perfectly at zero, but it will be close to zero when at the onset of the stimulus. So then you can see how does the pupil change in size as they're viewing the image. The other way you can do this as well is you can actually normalize the data completely by taking each value of the pupil size, subtracting the baseline, and taking that and dividing it by the baseline. So basically everything scales between 0 and 1. Yes?
And this is done for each trial.
This is done per trial.
Okay.
Yeah, this has to be done per trial. Okay, so what you have then is a change of pupil size, not the actual absolute pupil size. And so here again, you've now got, I've got blue being the hard, black being the easy condition. So you can see in the easy condition, pupil size is actually constricting over time. In a hard condition, this is over the 10 seconds of my trial. In a harder condition, I've got a dilation of the pupil immediately after the onset of it, and it's sustained for a long period of time and only starts to decline after about 5 seconds. So now you're starting to see, if you do this right, pupils' data can actually really be not that difficult to analyze. There's a few steps you have to do in order to get there. Once you have the data, there are then really sort of two ways in which you can analyze it. The first is actually quite simple, is to take time bins and kind of calculate the average pupil size over those time bins. So this is what you can do here. So here you've got 2-second bins. What you do is you take for 2 seconds worth of samples, you take the average pupil size, and you just plot that. So you can see here, the easy condition, the pupils are getting smaller as the trial goes on. In a hard condition, much like we saw on the data, you've got a pupil dilation initially, and then it starts to constrict after 8 seconds. What's nice about this, and why most people prefer doing this, is that you can just shove that in a simple repeated measures ANOVA, where you've got your problem or your manipulation in one group, and then a change in time over the other. Simple, easy, run an ANOVA, get your result. So that's how most pupilometry data is analyzed. However, you're throwing out a lot of interesting features here in terms of we don't know within that time window of 2 seconds what's going on. Sometimes we might want to link a particular pupillary response to a specific event that's going on the screen. So much like event-related potential in EEG, where you want to relate a particular change in electrical activity depending on what was on the screen at the time, likewise, you might want to do that with a pupillometry analysis. So you can actually do that, and this is the second way in which pupillometry data is now starting to become more commonly analyzed. And this is what's called functional data analysis. It's basically ripped directly from EEG. So these methods have been around since the 60s. It's common. What you just do is you subtract one pupil average from the other. So say, for example, hard minus easy. What then is you have the difference between the two. When you do that, what you see is this dotted line. You see this sort of variance between the two. So remember, at the hard conditions, they become more dissimilar, and then they start becoming more similar over time. The black line here is just a line that's fit, and it's actually a B-spline curve that kind of fits the average of that data. And so it's somewhat easier to kind of see that you see initially there's no difference between the two, but by about 5 seconds, 5.5 seconds, we're getting quite a difference between the two. And then that drops, and that becomes less different as they get towards the end of the trial.
Are we still doing this per trial, or can we do it
Per trial. You can average this up across conditions. See, this is you do this per trial. You average up the values, and then these are like grand averages.
So this is not a single participant's data?
No, this is across participant, across trial,
Okay.
across condition. You can then just shove that into a t-test. So what you have here is basically, you can test the null. So here the solid line here is the t-value beyond which the data are significantly different. So what you see is about 200 milliseconds into the trial, there's a small difference that occurs between the two. That's that initial pupillary response to the stimulus. Then they become very similar until about 4,200 milliseconds into a trial, at which point they become again statistically significantly different until about 8,500 milliseconds, at which point they become statistically the same. So again, it tells us that here, this is the initial response to the problem. Oh, I'm dealing with a hard problem, not an easy one. Then, as people start thinking through the problem, at this time point here, obviously the easy condition is people are already dropping off. That's where you start seeing the difference, the sustained response. So remember I talked about this phasic and tonic response in pupillometry. That is the phasic response, that initial dilation of the eye. This is more of a tonic response, a sort of a sustained dilation of the eye in response to the stimulus. These are two of the most common ways of analyzing the data, either binning or doing this functional data analysis. There are, every month or so now, there are more fancy, that people have used principal component analysis, they've used factorial, reverse, not correlation, convolution analysis. There are papers coming out all the time with fancier and fancier ways of analyzing the data. These two are the simplest, and they will help most people describe their pupillometry data. Okay, now the burning question that you all have. How the hell do you do this? Okay, it's really, you cannot do this in Excel. Okay, in the Dropbox, I can't remember if I've already put them up there. If not, I will put them up very soon. I will be putting up MATLAB scripts which will do every single part of this analysis for you. So all you have to do is point it to the correct columns in MATLAB, hit run. It will do the cleanup. It will do the filtering. It will do all of this and plot and do the analysis all for you without you having to think. If you're an R creature, there's this website here which does the exact same thing. It shows you how to run the exact same analysis in R. R is free. So again, all you have to do is copy their scripts, run them on your data, and it generates a pupillometry. So it really is easy. The only thing you're going to have to do is, so for example, the MATLAB scripts here are only designed to run on an iLink or a Toby. So if you're using an eye tracker that's different than those, you're going to have to just you have to make sure that the script is pointing to the right where the X and the Y values and the pupil size and the timestamp is for each of you. So there's a little bit of editing you would have to do. If you have problems with that, you can come and ask me and I can show you how you can fix that. But really, there's no excuses not to do this. And again, you can also correct for position on the screen quite easily as well, and the scripts are also in there in both of those as well. Okay. The only thing you have to do is on a few subjects, get a baseline, and you should do this on every single eye tracker that you run. You only have to do it once to get a map out for your particular eye tracker, your screen, your viewing distance, what is the screen, the pupil change over time on the screen. Once you have that, it'll never change. As long as you don't physically change your setup, it will never change. So you just apply that correction factor constantly. So about 20 minutes, half an hour of patience and running a few people will save you a lot of pain later on when it comes to actually publishing your data. Okay? It's 5 to 12. Any questions? Yes?
For those of us who are going to be doing pupillometry for projects,
Yeah. Yes. Okay. It's not that it looks. It's really just a series of steps you just have to follow through. Again, if you use the MATLAB scripts or the R scripts, this is all automated. What I'm trying to do is I'm trying to explain what the steps are in the code so that you understand what's going on. You should never blindly use anyone's analysis code. Always try and understand what it's doing at each stage. So what I've done today is taking you through what is going on in terms of the analysis and how you can correct for that, or how you would analyze the data. Okay? Right. So I'm going to take a